This is an example of what the sampling distribution can be used for. So just to repeat, we have a population with a mean, a variance, and a standard deviation. And from this population, we take an infinite number of samples of a certain size, and we calculate the mean of each of these samples, and from these means, we make a sampling distribution. And this sampling distribution will be normally distributed. The mean of the sampling distribution will be the same as the population mean. And the variance of the sampling distribution will be the variance of the population divided by the sample size. Therefore, the standard deviation of the sampling distribution will be the square root of this, which is the standard deviation of the population divided by the square root of the sample size. You should note that in statistical language, the standard deviation of the sampling distribution is sometimes also called standard error or standard error of the mean. And this is a term that you will come across several times. Now, what does this information tells us more? Well, we know that in a normal distribution, which the sampling distribution is, 95% of the values lies within an interval that is plus minus 1.96 standard deviations away from the mean. Therefore, we can say that if we take a sample from this population, in 95% of the cases, the mean of that sample will be within this interval. We're now going to look at an example to make this a little bit more clear. And we will use the numbers from box 8.2 in the book Statistics Explained by Steve McKillop, the 2011 edition. In this example, we have a population with a mean of 100, a variance of 1296, and therefore a standard deviation, which is the square root of this, that is 36. We also have a sample with a sample size 16 and a mean of 81. And the question we ask is it likely to get a sample mean of 81 if we take a sample of 16 from this population? Or is it likely to get a sample mean that deviates this much from 100, which is the population mean? We have a theoretical sampling distribution for a sample size of 16, and we can calculate the variance of this by just putting in our value for the variance of the population divided by the sample size. And we can also calculate the standard deviation of the sampling distribution by taking the square root of this, which equals 9. Now when we have the standard deviation, we can calculate these limits. So we just put in our values. The mean of the population, 100, minus 1.96 times 9, the standard deviation of the sampling distribution. And this equals 82.36. And similarly for the upper limit, 100 plus 1.96 times 9 equals 117.64. What does this tell us? Well, if we take a sample size, the sample of the size 16 from this population, and calculate the mean of this sample, in 95% of the times, we should get a sample mean that is between 82.36 and 117.64. In our sample, we had a sample mean of 81. This is outside these limits. And it means that it's a less than a 5% chance to get a sample mean that deviates this much or more from the population mean. And the most likely conclusion we draw from this is that this sample does not come from a population with a mean of 100 and a variance of 1296. You can come to the same conclusion by skipping over this underlying theory of the sampling distribution. And this is how it's done in the book. In the book, you simply calculate a z variable putting in your values for the sample mean, the population mean divided by the standard error or the standard deviation of the sampling distribution. This equals 2.11. And since this value, 2.11, is higher than our critical value of 1.96, we draw the same conclusion as before. It is not likely that this sample comes from this population.